Question for what system of numeration would be for what base? The system of numeration instruction is common in some of the older number theory textbooks. But for what base? Like, for example, Hindu Arabic is base 10. Now let's just take a look at this. 33 times 23, you can tell that's not equal to 1001 in base 10. Just to be clear, 33 base 10 times 23 base 10s. Now, we normally don't do it this way, but what it really means is this. That's equal to 3 times 10. I'll put a dot there, save some space. 3 times 10 plus 3. And let me get this parenthetically here. And then 2 times 10 plus 3. Now again, this is way too awkward to write out every time. That's why the shortcuts were invented to do this type of multiplication. But this is literally what it means. 3 times 10 to the first power. Just put it there for a little bit of emphasis. Now if you multiply that out, you'll end up getting, let me see, I wrote it down somewhere, 759. 759. So you see that's not equal to this number, okay? So let's see how we can determine what this would hold in some base is the claim, and the base would be a positive integer, okay? What we mean is just a positive integer. One's not so interesting, right? Positive integer. Positive int for the computer programmers. And then, so the work is, I've done most of the work already here, folks. Now, one thing to note right here, as far as understanding what I did here, 1001 base b is equal to 1 times b cubed plus 0, and let me write small here, plus 0 times b squared plus 0 times b plus 1. But you can see that that's where we get the b cubed right here, right? B cubed plus 1 is exactly this. All these zeros go away, and you just have b cubed plus 1. And it's similar for the rest of this, folks. For 33, it's 3b plus 3, 23, 2b plus 3. So I've done most of the work here. And we do end up with a third-degree polynomial, which has positive. We're not interested in any negative integer bases here. They make sense, but most people don't use them. And so you can rule out, you can look very quickly to see that 1 doesn't work, 2 doesn't work, 4 doesn't work. It doesn't take much time to verify that 1, 2, and 4 are not solutions to this equation. But right here, when you substitute 8 in, and again, here's 8 cubed, 6, 8 squared, 15 times 8. And let's just see what we get there. If that's going to work, that has to equal to 0. So I'll just do the simple factor out an 8 here. So if we factor out an 8, we have, 8 squared left here. And y'all, we would have 6 times 8 here, which would be minus 48. Okay. If we factor an 8 from this, you get minus 15 and minus 1. And that manifestly is, let's just come right here if I have room. That's equal to 8 times 0. 8.0 equals 0. So the missing base is 8. Now you can see how much trouble this would be if you went for a higher number of digits. If this was just 5 digits, you would, I guess, a quartic equation. And so we use what we call the rational zero theorem. This is the rational zero theorem, and the only possible rational zeros would be integers. You see there's an understood 1 here, and the possible rational solutions are all combinations of the divisors of the constant term over the coefficient of the leading term, but that's just going to be 1, 2, 4, and 8 as far as the positive side goes. So anyway, y'all, that does it. The answer to the question would be base 8. Let's just write right here, base 8. And again, that phraseology is not particularly popular these days. I don't think people just say, what's the base? But he's not raising too much of a disturbance, so it looks like we probably got it right. Thanks for viewing.